Chapter 5, problem 25.
Three rescuers are pulling horizontally on a safety net to keep it taut. One pulls northward with a force of 270 newtons. The second pulls on a direction 30 degrees south of west with a force of 240 newtons. In which direction and with what force must the third pull to keep the net stationary?
Okay, so I've got this safety net. I have 3 people pulling on it. I have 1 person pulling north with some force. We'll call it F1. Pulling north, force F1. I have another person pulling with a force, what is it, 30 degrees?
South of west.
South of west. Where is south of west? Which is this quadrant south of west? This quadrant? No, this quadrant? Yes. So this would be west. South of west would be 30 degrees south of that. So we do 30 degrees south of west. Okay. All right. And the final, so that we'll call that F2. And then the final thing that we're asked about is what is the direction and the magnitude of the force that the third person needs to pull to keep this thing taut. So which quadrant do I need to be in? 1, 2, 3, or 4? 1, 2, 3, and 4. I need to pull in 4. With some force F3 at some angle. I don't know what that angle is yet. Okay, so I have things acting at angles. What have I said about any time you have things acting at angles? What do? Break it down. Start breakdancing? No, I'm not going to break it down. So we start breaking it up into x and y components, right? So let's break this up into x and y components. We'll do all x components in, we'll do dark blue. So I'm going to have some little bit in the x direction, and I'll call that F2x. Some little bit in the x direction for F3, we'll call that F3x. So I'm just breaking these up into x and y components. Okay, so that's the x. Now I need to break up into the y. I have F2 going a little bit in the y direction. And I have F3 going a little bit in the y direction. How about F1? Where's its x component? Doesn't have one. It's going entirely in the y direction. Okay. So now when I want to actually solve this, I need to take this picture, keep it in mind, and I need to write things out in the x and y directions. So there's something new that this iPad lets me do. I'm experimenting with it, so we're going to try. Yeah, this might fail miserably. Let's see. I'm supposed to be able to shrink pictures and move them. Yeah. So we can keep that picture in mind. We can keep watching it. And then we can actually write out things going on in each different direction. So we can write out what's going on in the x direction. And we can write out what's going on in the y direction. And I want to sum up all the forces that are going on in each direction. The sum of the forces in the x direction has to be equal to the mass times the net acceleration in the x direction. How fast is this taut thing that they're throwing people onto? How fast is it moving in the x direction? Is it moving at all? So what's the acceleration in the x? 0. So the net force in the x direction has to be 0. What are the forces in the x direction? Let's plug those in. F sub x. Let's say anything that's moving to the right is positive. Anything that's moving up is positive. Anything moving in the opposite directions would then be negative. So which forces in the x direction are positive? F3x is positive. We can see that in our picture, F3x is moving to the right. Any other forces moving to the right? No? Any forces moving to the left? What's moving to the left? Okay, minus F2x. What does that equal to? 0. So we know F3x has to be equal to F2x. Yeah? When I'm writing these out, do I want to just leave them as F2x and F3x? What have we always been doing with these?
Just change the mass acceleration. F equals ma. Just replace these with
Ma. Were we given a mass and an acceleration? What were we given? We were given a force. What forces were we given? Were we given F1? Did they tell us a number for F1? What is it? 270. Did they give us a F2? Yeah? What did they give us? 240. Did they give us F3? No, that's what we're looking for. So I have F. What else do I have? What else did they give us? They gave us an angle. They gave us theta 2 is equal to 30. So can I write F2x in terms of F2 and theta? I can. How can I do that? What part of the triangle is that? F2x is right next to the angle, so F2x is going to be the adjacent side. What trig function is the adjacent side? Cosine. So that means F3x is going to have to be equal to F2 times the cosine of theta. We did this all last chapter. We're going to keep doing this nonstop, breaking things up into components. So I now know what F3x is. I'm looking for F3 though, right? So how do I get an F3 in there? How do I write F3x in terms of F3? Lots of mumbling.
F3x is
F3
cos with theta
cosine
divided by
theta 3 equals F2 times cosine of theta. Yeah? So I'm looking for F3. I'm looking for theta 3. I'm looking for two variables. Do I know what F2 is? Yeah, what's F2? 240? So why don't I plug in some numbers, because you like plugging in numbers, I'm sure. F3 times cosine theta 3 equals 240 times cosine of 30 degrees. Okay, so I have two unknowns in this equation. Two unknowns and one equation. What do I need to do to find the other unknown? I need one more equation. So I can look at what's going on in the y direction. What is going on in the y direction? Sum of forces in the y direction. I'm going to go straight and jump to say that that's equal to 0. Why is that equal to 0? Because it's stationary. Nothing's moving in the y. What forces are acting up? F1 is going upwards. If we can see that in our picture, that's the only force that's going up.
minus F2y
Minus F2y
and minus F.
minus F3y. Okay. Can I plug in some numbers? Can I plug in F1? What's F1? 270 newtons. F2y. Can I plug in anything for that?
Yeah.
240. Wow, that's some horrible handwriting. 270 minus 240 times what? Sine of 30. Minus f3y would be f3 times sine of theta equal to 0.
Isn't theta 3?
Hmm?
Isn't theta 3?
Yeah, theta 3. Okay, how many equations do I have? I have one equation here. I have another equation here. How many unknowns do I have? 2 unknowns. Can I solve those? In theory, yes, I can.
Well,
These things. We know that f3 times cosine of theta 3 has to be equal to f2 times cosine of theta, f3 cosine of theta 3. What was f2? 240. Cosine of the angle, what's the angle? 30. f3 times cosine of theta is equal to, let's plug that into your calculator. What number do you get for f3 cosine of theta? Yes? 208 newtons. We like numbers, right? f3 cosine theta equals 208. Yeah? All right. We have an equation in the y direction too, don't we? We have f3y equals f1 minus f2 times sine of theta. We just got that. What was f1? 270. Minus f2 is 240 times sine of 30. f3y. If you plug in everything and solve for f3y, what do you get? $150 newtons? Good, that's what I got too. Yeah? Yes?
When you wrote out the other term, wasn't it the F2 sine theta minus F1?
It would be f2 sine theta minus f1 equals negative f3y.
Because it would be
If we go all the way back to here.
F1 minus F2y minus F3y. So it's negative.
What do I know now in this picture? Do I know what f3x is? What is f3x? 208. Do I know f3y?
Yeah.
Yeah, what is that? f3y is what? Negative 150, because it's going down. Yeah? They're both in newtons. So these are making a triangle, aren't they? I have an f3x and f3y. 208, 150, and they're going to give me a magnitude of f3 and some angle. Can I find f3 from the numbers that I'm given? How can I find f3? Pythagorean theorem. So f3 is what? Square root of 208 squared plus 150 squared. Plug those numbers into your calculator. What do you get? 256. How do I find theta? Inverse tangent. Or sine, or cosine, any one that you want. If I use tangent, what am I doing? What's the opposite side? 150. What's the adjacent side? 208. 150 over 208. Theta is the inverse tangent of 150 over 208. And what angle do you get? 36 degrees. That is the entire problem worked out in insanely gory detail. Chapter 5, number 39. So in here, we're giving two chandeliers, right? We're given masses of each of those chandeliers. So let's write down everything that we know. We know the mass of this first chandelier is 10 kilograms. Bless you. We know the mass of the second chandelier is 3 kilograms. And we know that they're both hanging here. My chandeliers are ugly. They're boxes. That is the situation we have. First thing we have to do is draw a free body diagram. What does that mean? What is a free body diagram? Draw all the forces acting on it. What forces are acting on these boxes? Tension and gravity. Where does gravity go? Down. So I have gravity. Let's look at the bottom box first. I have gravity acting down on this box, don't I? So I'm going to identify gravity going down. With some force of gravity 2. Force of gravity on the second box. Yeah? Now, if there were no other forces acting on that box, what would happen to it? It would be falling down. Is it falling down? No. What force is keeping it from falling down? The tension. So where does the tension act? Up. We have tension in this cord. I'm going to call it T2. Any other forces acting on this second box? Normal force?
Or that's just on contact.
Normal force only acts when you have contact. Do we have contact of these things on a table or anything? So are there normal forces? Nope. Anything else? Nobody's swinging from it yet. The song hasn't started, so that they can't swing from the chandelier. First box. What are the forces acting on the first box? Gravity. Where does gravity go? Gravity goes down. So we'll call that force of gravity on the first box. What other forces are acting on the first box? The second box. And how much force is that applying? And how is that applying the force? Where is that force actually coming from? Where are you feeling that force? Maybe it's a bad way to phrase the question. It's the tension in the rope is pulling it down. Yeah. So we have T2 also acting down on the first box. So tension 2 is acting up on the second box, but it's acting down on the first box. Same tension, just acting different directions on the two different boxes. Yeah? Okay, right now it looks like we have two forces pulling down on that first chandelier. What direction would that chandelier be going? Down. This would make a good movie, good action movie. How do we keep the chandeliers from falling? We have another cable. What should we call that? T1. Whoa, brilliant. Ingenious. T1 acting up. Yeah? Any of this seem confusing so far? This is all pretty good? Okay. Let me erase. No! My eraser's not working. Maybe I can shrink. Shrink and move. You don't understand how awesome that feature is. None of my previous lectures I could do that feature, and this is great. Okay, so what should I do now? I did the free body diagram. That's part A. I just got a perfect score on part A. Hey. Now we have to do what?
You find the tension in each.
Find the tension in each chord. So I need to find T1 and T2. So I need to write down the sum of forces acting on each one of these chandeliers. Which chandelier should you start with? Why the bottom one? You have to add the bottom one to the top one, right? There's less forces acting on the bottom one, so start with the easier one. So let's look at box 2. What forces are acting? Let's write down our Newton's second law. Sum of forces acting on this box. I'm going to throw in a trick question. What is the sum of forces acting on the box in the x direction? 0? Why is it 0? It's not swinging back and forth. It's 0. We don't need to worry about it. I'm just going to erase it. We need the sum of forces in the y direction acting on this box.
0.
Yeah, 0?
Yeah, it's not moving.
Yeah, because it's not moving. Okay. How does that help us? Does that help us at all?
Yeah.
It does. What else do we need to do, though? We need to actually identify the forces in the y direction, right? Let's explicitly write them out. What forces are acting to pull that second chandelier up? T2 is acting up on the second box. What forces are pulling it down? Fg2 has to be equal to 0. So tension 2 has to be equal to Fg2. Tension 2 has to be equal to Fg2. What is Fg2? Mass 2 times gravity. Do I know what mass 2 is? Yes. Do I know what G is? Yes. Can I find what T2 is? Yes. Let's actually plug in our numbers and find what T2 is. T2 has to be equal to M2, which is 3 kilograms, times G. What is G? 9.8 meters per second squared. Why didn't I plug in a negative? Well, first question, what is 3 times 9.8? 29.4. We just did that in our head. Okay, so I now know what the second tension is. But why didn't I say that G is negative? Why didn't I plug in a negative number there? Hmm? So it's a positive force, okay.
Can you have a
I thought G was always negative, though. Why isn't it negative here?
Can you have a
Because you added it to the other side, it was negative.
Yeah, but here, tension 2 is pulling it up. Yeah? Fg2 is pulling it down.
But you moved it to the other side.
So why do I not plug in a negative here? Let's look at what I actually did, right? So I already accounted for the negative when I wrote this out. I accounted for the direction of everything acting. Yeah, in the acceleration equations, when you're plugging those in, usually you haven't accounted for the direction explicitly in writing out those equations. Yeah, so you need to plug in a negative. So in the 1D equations of motion, you're usually plugging in a negative G. In the force equations, when you are using G in force problems, you account for the direction when you're writing out this sum of forces. So plug in a positive G. Okay? Okay. Now let's do box 1. What are the forces acting on box 1? What forces are pulling it up? Let's start at the beginning. Sum of forces on box 1. What is it? Is box 1 moving? 0. What force is pulling it up? T1. Any other forces pulling up? No. What forces are pulling it down? Fg1. And what else? And T2. Anything else? Isn't Fg2 pulling it down? Fg2 is pulling it down in the form of T2. Okay? So T2 is the force of the second box. So T1, which I'm looking for, is equal to Fg1 plus T2. T1 equals Fg1. What is Fg1? What is Fg? mg. Dear God, we should all know that that's mg. I don't want to stand up here and chant that anymore. m1 times g plus T2. T1 is equal to m1, which is 10 kilograms, times g, which is positive or negative? Positive 9.8. Why? Because this is a force equation. We accounted for direction already right up here. And then plus T2. What's T2? 29.4. Plug in these numbers. And what do you get? You got what? Say that again. I just didn't hear. 127. Okay. Chapter 5, number 71. We have the world's most demented stick figure woman with the longest arms imaginable and a very bad haircut pushing a box up an incline. Yeah? Yes?
How is she pushing a box that on a slope that doesn't have any friction on it?
She's wearing fancy shoes that provide friction. Her feet have friction. I don't know how she's doing it. She's magic. Here. She's a wizard. Or I guess it'd be a witch. Okay, so we have a witch that is pushing this box up by flying on her broomstick.
Yeah, that's a thought.
Okay. So that's a good question. That is a very good question. So we have a witch pushing the box up apparently. And she's pushing horizontally on this box. The first question we are asked to do is to draw a free body diagram of all the forces acting on this box. What are the forces acting on the box? You already said gravity. Where does gravity go? Straight down? Straight down. What's the letter for gravity? Fg. And what is Fg? It's frickin' mg. Fg is mg. Did they give us a mass for this box? Yep. Yeah? So what's the mass of the box? 60 kilograms. And we all love plugging numbers in as quickly as we possibly can. So go ahead and plug your numbers in. Find what Fg is. What is Fg? Roughly 600. What is it? 588. Okay. Did we have to find that number right now for part A? No. What did part A ask us to do? Just the free body diagram. Are we done with our free body diagram? What other forces are acting? The what force? Normal force. Every year, about half the physics class calls it the natural force. I don't know why. I don't think I say natural force in the lecture at all. I should rewatch it. Yeah? Puppies and kittens.
People laughing.
People laughing. My wife. Yeah. I'm doing physics, how could it not be fun? Where does so there's a normal force acting. Where does the normal force act? Yeah? Is that a question? Perpendicular to the incline. It's an answer. So what is perpendicular to the incline? How do I draw that? This way, okay, yeah, yeah. So we have this normal force, Fn. I call it the Fn force. Okay. Anything else for our free body diagram? Yeah, now you're all going to call it natural force. Yeah. Gives me points that I can take off. The challenging part of these kinds of problems is figuring out the coordinate system to use. Right? Normally, you write out your coordinate system and you just have x and y. Yeah? If I do that, if I use x and y, then I end up with things acting at angles. I don't want that. So usually what you want to do in these problems, and I'll suggest it in this problem, is you take this coordinate system and you rotate it. Actually, I can maybe show you that. So this is your normal coordinate system, x and y direction. You take this coordinate system, up, don't want to do that, and you spin it around. So you take this coordinate system and you rotate it 45 degrees. Yeah. So instead of your coordinate system going up and down, the coordinate system goes up and down the incline. So what you want is a coordinate system that acts like this.
Wouldn't it be 30 degrees and not 45? No?
So yeah, I guess you rotated 30 degrees. So let's rotate that, use that as our coordinate system, a rotated coordinate system. And let's break out our pieces into their components along this new coordinate system. Which of these forces do I need to break up into components if my coordinate system is this rotated one? Do I need to do anything to the Fn force? Nope, because it's acting entirely in the y direction. It has no components. What about the push force? That is now acting at an angle. I need to break it into the x and y components. So I have one piece that's going to go along the incline. We'll call that Fpx. And I have one piece that's going to act downwards. What shape did I just draw? Triangle. I probably need an angle in this triangle. Do I know any of the angles in this triangle? That's going to be 30 degrees. Yeah. Okay? All right. Let's look at Fg force of gravity. Do I need to separate this into components? Well, this is at an angle with respect to my new coordinate system too, so I need to break it up into components. I need to have one that's perpendicular to the incline. Make that Fgy, and one that's parallel to the incline. That's Fgx. Do I know any of these angles in this new triangle? Right, I have this triangle for gravity. Can I figure out any of these angles? Yes, Albert.
The one at the top?
The one at the top.
So
This one?
Yes.
Okay.
30, because the opposite on that one has to be 60, because the other one was in there.
Okay, so let's see if I can follow this. Whew. So you're saying this angle right here is 30, yeah? So then this angle you're saying has to be 60?
Yes, because those.
Because this is a right angle.
Yeah.
Yeah? Okay, so then if this angle is 60, And then this angle here is a right angle. 60 plus 30 gives me my new right angle, gives me my triangle. Welcome back to geometry. Okay. Now, using all of this information, I can actually completely solve this problem. And we will do that next time. So we'll start recording, and I will include this onto the video for this class that's already posted up. Okay, so you have the incline. The incline is 30 degrees. You're pushing this box with the horizontal force, F push. We had the force of gravity, and we had the normal force. What's the name of this diagram that we drew? Free body diagram. We identified all the forces. What did we do with those forces? Broke them up into x and y components. And where are our x and y axes? Tilted along the incline. So we have an xy axis that looks like this. There's our x, there's our y. Yeah? So I need to break things up into x and y's. We have our F push. We had some x direction, F push in the x direction. We'll call that FPX. And we had some push in the y direction. We'll call that FPY. What else did we break up into x and y components? FG. We had FGX. So let's say maybe FGX goes like this. And we had FGY. Now is this the exact same picture that we drew last time? Yes? How do I find these angles? Which angle's the easiest? I think this angle is probably the easiest to find. What is this angle? Or maybe if that's not easy, maybe this one's even easier. 30 degrees. So that's going to be a 30-degree angle. And what one?
Where F of Rx and F of Py meet.
I have no idea what you're saying.
It's the right angle.
That's the right angle. That's a right angle.
I don't think that.
I'm talking about
The corner one.
Yeah.
Where the.
there.
That's a 90-degree angle. Perfect.
That's what I'm talking about.
Okay. So what's this angle?
Which one?
This one.
That's
60. Okay, let's figure out the other triangle. We already have an angle for this one. Let's use the 30-degree angle there. We have this triangle. What are all these angles? How could we figure these out? So this is a 90-degree angle, right? This is a 30-degree angle. So that means all of these angles added together have to be what? 180. So if this is 30, this is 90, how big is this? 60. So let's use this one is 60 degrees. This is the hardest part of physics. Going back and dragging everything you learned in geometry from back in high school. It all comes back. Okay? So now we have all these triangles, we have all these different components. We can start to actually solve this problem. We can figure out what these forces are, what the normal force is, what the force that we're pushing with is, everything we want to know. How do we figure out everything we want to know? What do we do with force problems when we have things acting in x and y? Split it into the x and y direction. What's going on in the x direction? The sum of forces in the x direction. Let's say anything going up the incline is positive. What is going up the incline? FPX. Anything else going up the incline? No? Anything going down the incline? FGX minus FGX. That has to be equal to the mass times the sum of the accelerations in the x direction. How fast is this box accelerating in the x direction? Up this incline. Remember from the problem what the acceleration is. This magical witch is pushing it upwards at a constant velocity. So acceleration is 0 because the velocity is not changing. So that means all of this is 0. Yeah? Okay. What do we do with FPX?
We can say that FPX equals FGX.
FPX is equal to FGX. Perfect. And what I want to do is I want to write these components in terms of the actual forces that I'm applying. So I want to write FPX in terms of FP, and I want to write FGX in terms of just FG. And I can do that using the trigonometry of the triangles that I've drawn. What is FPX inside of that triangle? There's FPX. There's 30 degrees. There's FP. What side is FPX relative to that 30 degrees? It's the adjacent side. So FPX is going to be equal to FP times the cosine of 30. FPX is FP times the cosine of 30 degrees. We can do the same process for FGX. What is FGX? Let's draw the FG triangle. FG is going down. There's our FGX. There's our FGY. This is our angle, 60 degrees. What is FGX relative to that angle? It's the adjacent angles. So what trig function do I use? Cosine. FGX is equal to FG times cosine of what angle? 60 degrees. And it's all getting all nice and jumbled. FG times cosine of 60. Can I simplify this anymore? Can I write FP any differently? I'm going to go with no. FP cosine of 30. FG, can I write that any differently? What's FG? MG. Yeah? So now I'm looking for the force that I'm pushing with. So FP is equal to M times G times cosine of 60 divided by cosine of 30. What's M? Do I know what M is? M is 60. Do I know what G is? 9.8. Why did I not plug in a negative? I already accounted for it right up here. When I said that FGX is negative, that accounts for the negative. So I just plug in positive 9.8 meters per second squared times cosine of 60, all divided by cosine of 30. And what's that clicking sound that I hear? It's a calculator. So what do you do with your calculator?
Use it.
Plug in the frickin' numbers and you get a frickin' answer. What frickin' answer do you get?
340. Use it. I actually said 340.
339, 340. So we found our F push. Same exact process for the y direction. For the y direction. Sum of forces in the y direction. If we look at our picture, we have a normal force going up minus F push y going down minus Fgy going down the incline. Is it accelerating as it's going in the y direction? Nope, so that's equal to 0. So I have my F in force, normal force that I'm looking for, minus F push y is going to be Fp times sine of 30, Fgy is going to be mg times sine of 60. Has to be equal to 0. I can get Fn by itself by adding both the force of the push and the force of gravity over to the other side. So I get the Fn force is equal to Fp times sine of 30 plus mg times sine of 60. Let's see if I can plug in any numbers and make this easier. Fp, do I know what Fp is? Yeah, what is it? 300, I'm going to switch, 340, 339. What are the units there? Newtons, because it's a force. Times the sine of 30. Plus m, do I know what m is? Still 60. 60 what? Kilograms. What's g? 9.8. Why isn't it negative? Because I accounted for the negative right there when I said Fgy is negative, times the sine of 60. Plug in all those numbers, and you get that your normal force will be equal to 679 newtons. So do the exact same process in the x direction and in the y direction. Breaking things into components, x and y separately, and then just solve it out. Best way to get good at these, practice.
What was the initial question for this problem? Was it just to find the F?
Find F push and the normal force.
Oh, okay. So that's what
Yeah.
basically identified the variables. Okay.
Yeah. Okay. Any questions?